Hello, this is Muneer from Jordan University of Science and Technology. Today I'll be showcasing my nonlinear finite element flexure analysis of RC beams after the work of the researcher Mazen Musmar. Now he analyzed this RC beam using ANSYS software. I'll be doing the same using Abacus 19 software. All right, so now to start with the model, I first start by creating the parts. First of all, this is the RC beam itself. This is the concrete part, and then I mesh it to 50 millimeter mesh. And then I created the plate. Now I will assume that the load will be transmitted through plates here as distributed pressure to avoid the concentration of stresses. After that, I have defined the steel reinforcement. We have steel of 10, 12, and 14 millimeter diameters, and then we have the stirrups. Now, these parts are meshed to 50 millimeter mesh. Now, after creating the geometry or the parts, I have worked on the material. I have defined the concrete material to have a density of 2.4 to the power minus 9 a ton per millimeter cubic. This is its density, and then I have defined its elastic properties based on the researcher information, and then the concrete damage plasticity. These are typical value for such cases. After that, I have defined the concrete compression damage and concrete tensile damage, assuming that the plasticity of concrete and compression will start after 0.45 FC prime, and the concrete plasticity in tension will start after reaching 0.1 FC prime. Now, after the materials definition, I started working with sections, and section is just assigning the materials to the geometry or to the parts that I have created. After that, I worked on the boundary conditions. As for the boundary conditions of this beam, we have a pin right here. The pin will restrict the movement in the 3 directions and will allow the rotation, while we have a roller here to the right that will prevent the movement in the Z and Y direction, and it will allow it only in the X direction, and it will allow rotation as well. Now, for the bond between the concrete and the steel beams, they are of embedded region type. We assume here the full bonding between both of the steel and the concrete, while in the plates here, we assume that they are just tied together, and this is to prevent the plates from restraining the beam from movement for the upper plates and just work as load transmitters. Now, after that, I have created a job to analyze this beam, and I have the results right here. So as for the results of analysis of this beam, as for the deflection here, U2 is for the Y direction. We can see how the deflection starts to propagate, and it has its maximum value at the middle of the beam. Now, the negative values here just indicate downward direction. And here we can see the propagation of cracks as the load increases. Now, as for the curves of displacement versus force, I have displacement versus time, this curve, and I have the force versus time curve. I have taken these two values or these two curves values to Excel, and I have created another model with a 25 millimeter mesh and 50 millimeter mesh. So, and I plotted the displacement versus force for each model, and I have these results. Now, they look similar to the researchers with minor differences, and I would suggest that the differences will go back to the fact that the type of solid element that the researcher that have used here is different from the one that I used. I used linear analysis, he used quadratic analysis. Here we got 25.2 millimeter deflection when using the 50 millimeter mesh, and we got 26.9 millimeter deflection when using the 25 millimeter mesh, which is the closest to the researchers' results here. And from this demonstration, we can see that the failure mode of this beam is flexural failure mode.